Welcome to Properties of Light. So, let's go over some terminology first. Spectrophotometry is any technique that uses light to measure chemical concentrations. Colorimetry is a spectrophotometric technique based on just visible light. So, colorimetry is a subset of spectrophotometry. Now, light can be described in terms of both waves and particles. Light waves consist of perpendicular oscillating electric and magnetic fields that you see over here. So as the electric field is oscillating in this direction along this axis, we see that the electric field is alternating up and down as the magnetic field is alternating left and right. And so you see that as the electric field gets larger, the magnetic field gets larger as well. And then as they pass through zero, they're passing through zero together, and then they're at their minima, and then they go back to zero, pass through zero, go up to the maxima, and so on. And so in this way, we have waves. So light can be treated as a wave like this, or we can treat it as a particle like a single photon. The wavelength, which we symbolize with the Greek letter lambda, is the distance from a point on one wave to the same point on the next wave. So if we sort of freeze our electromagnetic wave for a moment, and we go from some point, let's pick the peak, to the same point on the next wave, so the peak over here. So note that we're not going to the peak on the red curve there, because the blue curve is going down to its minimum, and then back up to the maximum, and so on. It'll keep going. So, the wavelength is the distance from crest to crest, or trough to trough, or from where it crosses the zero going down to where it crosses the zero again going down, or going back up, or so on. So the SI unit of wavelength is the meter, but often we describe wavelength in terms of other units such as nanometers. So now frequency, which is symbolized with the Greek letter nu, I know it looks like a little scripty V, but it's actually the Greek letter nu. Frequency is the number of oscillations the wave makes in some given time, usually per second. So the SI unit of frequency is hertz, defined as one oscillation per second. So a hertz is 1 per second. Now wavelength and frequency are related to each other via the speed of light. So c is equal to lambda nu, where c is the speed of light in a vacuum. In a medium other than vacuum, light travels at a slower speed, given by this equation. So the speed that light is propagating at in that medium is equal to c, the speed of light in a vacuum, divided by n, where n is the refractive index of that medium that the light is passing through. And while it's possible for n to be less than 1, it generally doesn't happen in the visible region of the spectrum. And so a good rule of thumb is that n is greater than 1. And thus, visible light travels more slowly through matter than through a vacuum. But wait, you might say, if n is less than 1, that means that the light can be traveling faster than c. And doesn't this violate the theory of relativity? In fact, no. The phase velocity, or how fast the wave crests are traveling, can in fact be faster than c. But the signal velocity, that is, how fast information travels, cannot. So this is one of the keys to the theory of relativity, that the signal velocity, how fast information can travel throughout the universe, is fixed at no faster than the speed of light in a vacuum. And so we can in fact get the phase velocity faster than that in some materials under some conditions, but we cannot have a signal propagate faster than c in any conditions. When light moves between different media, the frequency remains constant, but if the speed is changing, that means that the wavelength must change. So we can also think of light not as waves, but as discrete particles that we call photons, and the energy of a photon is directly proportional to the frequency, so energy is equal to h nu, where nu is the frequency and h is Planck's constant, which has the value of 6.626 times 10 to the minus 34 joule seconds. And we can also relate the energy of a photon to its wavelength then, So E equals hc over lambda, which is hc times nu. This little squiggly tilde is called the wave number. So Planck's constant times the speed of light in a vacuum times the wave number of light. Now, energy is inversely proportional to the wavelength. It's directly proportional to the wave number and the frequency. Wave number is generally expressed in inverse centimeters or reciprocal centimeters or wave numbers. And here we have the electromagnetic spectrum. On the right side here, we have long wavelengths, and these are things like radio waves. And as we move to shorter wavelengths, we get to microwave, and then infrared, and then the small visible region of the spectrum, and then ultraviolet, X-rays, and gamma rays. So again here, this line is showing the wavelength, and the wavelength is decreasing as we move to the left, increasing as we move to the right. The frequency is increasing as we move to the left, decreasing as we move to the right. Up here at the top, we've got energy. Energy is increasing as we move to the left, decreasing as we move to the right. And then down here we see, we've pulled out the visible portion of the spectrum. We have red down here at around 650 nanometers. Orange, yellow, green, blue, and violet is down at around 400 nanometers. And so then up here, we can see that over here we have rotation. So things like microwave radiation is stimulating rotational motion of our molecules. Infrared is stimulating, in general, vibrational motion of our molecules. The visible and ultraviolet are stimulating electronic transitions. So we are transitioning an electron from one orbital to another, to an excited state. As we transition to higher energies than that, we get into X-rays, which are breaking bonds and ionizing molecules and atoms. And when we get to even higher energy than that, then we're still able to break bonds and ionize. So the names of the various regions in the electromagnetic spectrum are historical. That is, there are no discrete changes in properties of light as we change from one region to the next, as we move from the radio waves to microwaves, to infrared, to visible, to ultraviolet, to X-rays, to gamma rays. There aren't discrete changes where we say, oh, well, that one is clearly an X-ray and this one is a gamma ray, and there's some distinct difference between them. There are no clear cutoffs. The energy changes, and as we move from one phase from one region to another. So that was properties of light.